All right, let's kick off. Hello, everyone, and thanks for joining me today on post-transformer AI architecture. In this session, we are going to explore what's emerging beyond the transformer, which was a generation of AI architecture. And we're going to cover things like mixture of expert, state space model, diffusion, RAG, and also brain inspired systems like SNN. So this presentation is not just about the technology, it's going to help you better understand how all these architecture map to real world use cases and how organizations, researchers and builders can make strategic choice in post-transformer world. So this is going to be the agenda. So as you can see, we're gonna start with a quick context. Then we're gonna dive deep on each of these AI architecture, and then we're gonna do some level of analysis and comparisons, and we will conclude with some of key takeaways. All right, let's start with the context. So what we've seen since 2017 is a major shift in the AI landscape. So the transformer architecture, which was the dominant model, is no longer the only game in the town. So while it was a good breakthrough, there is a quadratic complexity for this architecture, meaning that the computational cost scales with the square of the input length and the context window, and that's actually pushed the field toward more efficient alternatives. So there are like when it comes to the AI, we have different stakeholders, and the stakeholders in the AI ecosystem are now being called to act strategically and also differently. So for enterprises, the priority is now to build hybrid composable AI stacks. That means going beyond just monolithic solution and also invest in foundational enabler like clean AI ready data and also robust MLOps infrastructure. For investors, there's a shift in their focus. So there is more focus toward technologies that solve concrete downstream problems, especially those that address real enterprise pain points. So the edge of betting on general purpose model is giving way to a more targeted value-driven approaches. For researchers, the challenge is to architect hybrid systems that combine the base of various paradigms, whether it's combining symbolic reasoning with neural network or merging efficient models with high-performing one. Innovation now lies into integration, not just reinvention. So now let's go through these different architectures. We'll start with the transformer one. So the transformer architecture was introduced in the 2017 paper, Attention is All You Need. And it actually fundamentally changed how we approach sequence modeling by replacing recurrence with self-attention. So this shift allows model to process sequence in parallel, capture long-range dependencies more effectively, and scale massively, laying the groundwork for today's large language model. So the transformer did not just improve performance, it actually reshaped the trajectory of modern AI. While the transformer self-attention mechanism is powerful, it comes with a major trade-off, quadratic complexity. In simple terms, as the sequence length increases, the compute and memory requirement grow exponentially, making it incredibly costly at scale. This becomes a real problem in practical scenarios. You can think about long document, extended conversation, or model that need to handle large context window. The resource required quickly become unsustainable, especially at the scale. So the very things that made transformer revolutionary is now one of the biggest constraints driving new innovation. Let's quickly touch on the transformer architecture, strength, weaknesses, opportunity, and threat. So starting with the strength, transformer are proven foundation for modern AI. They power the breakthrough in language, vision, and beyond. But the weakness, the well-known OT2 time complexity that we already discussed, and also transformer requires significant memory, especially as context window grows. On the opportunity side, there is still room to evolve. We are seeing innovation like hybrid architecture, memory compression, and more efficient training techniques that aims to extend the transformer reach without sacrificing the performance. And finally, the threat, new architecture like Mamba and other linear time models are emerging with more efficient scaling properties. Now let's talk about the mixture of expert, or MOE, which is a clever architecture shift designed to tackle efficiency challenge in the transformer ones. So instead of using a single dense feed-forward network, MOE introduced sparse expert layer, where only a subset of the model expert are activated for a given input. This approach dramatically improved efficiency. It allows the model to scale in terms of capacity without a proportional increase in compute. In other words, you get the benefit of a much large model, but you are only using a small fraction of it at a time, making it far more resource friendly, especially in inference use cases. So now let's talk about how MOE works. So there is like three main steps. So there is a router selection. So a gating network evaluate each input token and dynamically select the top K expert best suited to handle it. So instead of passing the input through every expert, the model intelligently routed to just a few. Step 2 is sparse activation. Only those selected experts are activated. This means that although the model may have billions of parameters, only a small portion are used at any given time. And then step 3, load balancing. So to keep things running smoothly, load balancing mechanisms are used. So these prevent certain experts from being overused while others sit idle, ensuring that the training remains efficient and also stable across the board. Let's touch on a quick good example. So the mixtural 8x7B model. It has a total of 46.7 billion parameters, but only 12.9 billions are activated for any given token. That's the power of sparsity. You get the scale and on a huge model, but you are only using a fraction of it at a time. The result is up to 5x faster inference compared to a dense model. So MOE occupies a unique strategic position in the AI architecture landscape. The key advantage is clear. MOE models deliver high quality output that rival massive dense model, but with the inference speed and efficiency of much smaller model. However, the production reality is more complex. Deploying MOE models introduce challenges like communication overhead across distributed system and routing inefficiencies that can lead to underutilized expert or uneven training. So while the architecture is promising, successful deployment still requires careful engineering and also infrastructure investment. Let's touch on this problem in more detail. So while MOE offers impressive performance, it's not without the challenge, as we already mentioned. So there are memory requirements. Even though only a few experts are activated at a time, the entire model still needs to be loaded into the memory. And that can be a serious bottleneck, particularly in a resource-constrained environment. Also, we have training complexity. So routing token to the right expert is not always perfect. You can get imbalanced expert usage or inconsistent learning across different parts of the model, which can hurt performance and also stability. Finally, there is communication overhead. So in distributed setups, sparse activation lead to complex data dependency across devices or nodes, which increase latency and complicates system design. Alright, now let's talk about the diffusion model, which have quickly become a stand out in the world of generative AI, especially for creating high quality images and audios. So diffusion models work by starting with pure noise and then gradually denoise it over many steps, learning how to reverse the noise process and recover structured data. This iterative refinement is what enables them to generate incredibly detailed and also coherent output. The result? So some of the most realistic and high quality content we've seen from generative model to date, making diffusion models the go-to approach for tasks where output quality really matters. So let's quickly touch on the diffusion process. So first, there is this forward process. Gaussian noise is progressively added to the training data over many steps. By the end of this process, the original signal is completely buried in the noise. Then we have training. During training, the model learns to reverse the process. It trains to predict and remove the noise at each step, essentially learning how to recover the original data from the noisy version. Then during generation, we do the reverse. We start with pure noise and iteratively denoise it using the trained model. Step by step, the noise is transformed into realistic, coherent content, whether that's an image, audio clip, or any other modalities. So recent innovation have taken diffusion model to the next level, starting with the diffusion transformer or DIT. Traditional diffusion models rely on convolutional units, but DIT replaced the vision transformer. So this change significantly improves the scalability and also performance, especially for high resolution image generation. It also opens the door for more flexible architecture in other domains. Building on that, we have Multimodal DIT or MMM DIT, which introduce separate weight for image and text input, but merge them through shared attention layer. This allows the model to effectively align and generate across different modalities, improving result in tasks like text-to-image synthesis. All right, now let's talk about the RAG. So Retrieval-Augmented Generation RAG, which makes a major evolution in how we use large language model. So instead of really relying solely on what models was trained, RAG allows to dynamically pull the external information and transforming it from a static knowledge base into a real-time reasoning engine. Whether it's retrieving document from a private database or live web content, RAG improve both accuracy and also relevance, making it especially valuable for enterprise use case, search application, and any scenario where up-to-date context is critical. So in terms of the RAG pipeline, there are three main steps. We have indexing, where the first step is to prepare the knowledge base. So documents are chunked into smaller passages and then converted into vector embedding, which are stored in a search database, typically a vector store. Then in step 2, which is the retrieval, a user submit a query. It then converted into an embedding. Then system perform semantic search to find the most relevant chunk based on the meaning, not just the keyword match. And the final stage is the generation. Those received chunks are fed into the LLM along with the user prompt, and then these augmented context help the model generate response that are both coherent and also factually grounded in the most relevant source material. So in terms of benefit and challenges, on the benefit side, RAG drastically reduce hallucination by grounding output data or outputs on the top of these real context data. It also provides access to real-time and proprietary information without requiring costly model retraining. But on the challenge side, the quality of the output heavily depends on the retrieval system. So if relevant documents are not found, the model won't have the right context. Chunking strategies also matter. Too large chunk, you may lose the precision. Too small, you may lose the meaning. Plus, the retrieval can introduce noisy or irrelevant information, and it adds latency to the pipeline, which can affect responsiveness. Let's talk about now state space or SSM, which are emerging as serious competitor to transformer, especially for long sequence tasks. Models like Mamba offer a key advantage. They process sequence in linear time, compared to the transformer quadratic complexity. This means that they're significantly more efficient, especially as input length grows. Another difference is the architecture. So instead of relying on attention mechanism, SSMs maintain fixed size hidden state, which makes them better suited for streaming, real-time application, and also scenario where with memory or compute constraint. In short, SSMs are challenging the notion that attention is always necessary for sequence modeling. So let's talk about the Mamba and compare it with the transformer. So first, time complexity. So as we mentioned before, Mamba operates in linear time while transformer is scaled quadratically. Next, memory usage. Mamba used a fixed size state, which keeps memory constant regardless of the input length. But in contrast, transformer rely on a growing key value cache, which gets expensive fast as the context length increases. When it comes to the long sequences, Mamba can be up to 5x faster for inputs over 2000 token, where transformer starts to struggle with scaling. And finally, training speed. So Mamba leverages parallelism convolutions, which improves efficiency without sacrificing sequence awareness, while transformer rely on standard parallelism with attention layers. Alright, multimodal architecture, which are pushing the boundaries of what AI system can do by processing text, image, and audio with a unified framework. So at the core of this system is a shared embedding space, a kind of common language that allows different types of data to interact seamlessly. So this enables a model, for example, analyze an image, understand related text, and even interpret the audio, all in context with one another. So whether it's an image understanding in vision task, natural language processing for text, or a speech and sound analysis in audio, multimodal models are designed to fuse these input and reason across them, opening the door for more intelligent context-aware application. So in terms of the advantage, there is like a unified understanding here. By drawing context from text, image, and audio simultaneously, this model can interpret information more like a human do. And also, there is a simplified architecture. So instead of building and maintaining separate model for different data types and modalities, you get a single model and often a single API that handles multiple modalities. That greatly reduces integration complexity and also speed up deployment in real-world application. Alright, now let's talk about another interesting AI architecture, spiking neural network, or SNNs, which represent a fundamentally different approach to AI, one that is inspired by how our brain works. So unlike traditional neural network that process information in continuous signal, SNNs rely on event-driven computation. Neurons only fired or spark when a certain threshold is reached, and spark timing itself carries information. This allows for incredibly efficient low-power processing, making SNNs specifically promising for edge device and neuromorphic hardware. In short, SNNs aims to bring us closer to the brain-like computing, where energy efficiency and also temporal dynamics are key advantages. So neuromorphic computing brings a set of powerful benefits that mimic how the brain operates, starting with ultra low power consumption. In this system, only the active neuron use energy, which leads to significant efficiency gain compared to classic architecture like transformer. Also, there is the high level of parallelism. Neuromorphic hardware process information in an event-driven, massive parallel fashion. This allows for fast, low latency responses, ideal for real-time application like robotics or sensor networks. Finally, one of the most distinctive features is integrated memory and computation. So instead of separating processing and storage like traditional compute, neuromorphic systems co-locate both at the neuron level, drastically reducing data movement and improving speed and efficiency. In terms of challenge, so while this model holds a lot of promises, there is a still significant challenge holding widespread adoption. First, there is the ecosystem immaturity. Tooling frameworks and hardware support for SNNs are still developing, and there is a lack of a standardized benchmark, which makes it difficult to evaluate and compare models. Second, the learning curve is steep. SNNs require a different way of thinking about computation and training. Concepts like spike timing and temporal encoding and complexity that many teams aren't yet equipped to handle. Lastly, there are accuracy trade-offs, especially when converting from traditional neural network to spiking equivalents. Maintaining performance during this conversion is still a technical harder in many cases. All right, so we covered all these key architecture. Let's just go through the key takeaways of this presentation. So this is the AI architecture decision matrix that can help you translate complex technical trade-off into clear, actionable choices for business and engineering leaders. So each architecture here offers distinct performance characteristics across latency, throughput, and use cases. So transformer strike a balance, medium latency and throughput, making them ideal for general purpose language model and tasks requiring complex reasoning. MOE delivers low latency and high throughput, making it great for large scale inference where efficiency at scale is key. Diffusion model, while powerful for content generation, come with high latency and low throughput, best suited for non-real-time creative tasks. RAG combines generation with external data, so it often has medium to high latency and also is ideal for knowledge-intensive application, things like customer support or enterprise search. SSMs like Mamba model excel in long context tasks with low latency and high throughput, especially where sequence efficiency is critical. And finally, SNNs stand out for ultra low latency and also ultra high throughput, making them well suited for real-time, low power edge computing. All right, now let's just map where these key AI architecture and technologies currently sit on the 2025 hype cycle. So we start with the technology trigger. Here we have spiking neural network and neuromorphic computing. These are inspired by biology and often huge potential for low power real-time processing, but the ecosystem is still early and underdeveloped. Next, we have the peak of inflated expectation where hype outpace reality. AI agent and multimodal architecture are here. There is a surge of excitement around their potential, and but concerns like governance, safety, and complexity are starting to surface. Then the next one, through of this illusionment. So we have generative AI here. And then on the slope of enlightenment, we have transformer, diffusion model, and RAG. These technologies are no longer experimental. They are being refined and successfully integrated to real-world use cases. And finally, we have plateau of productivity, where we have all these MLOps and AI engineering. These are the tools and practices making AI sustainable, scalable, and also enterprise ready. So in terms of some strategic recommendation, so for enterprises navigating the evolving AI landscape, first build an AI ready foundation. This means investing in a strong data infrastructure and AI engineering capability. Then embrace composability. Don't rely on one size fits well model. Instead, build platform that integrate based of breed component. And finally, focus on scalability, choosing architecture and tools that can evolve with your business needs. So similar recommendation for researchers. So the most impactful innovation are emerging at the intersection of architectural families. So combining the strength of transformer, MOEs, state space model, and even brain-inspired approach like SNNs. This kind of hybrid thinking is where the real breakthrough are happening. Equally important is the push to bridge theory to practice. We need more than papers. We need tools, benchmarks, and frameworks that make it easier to bring experimental ideas like neuromorphic computing into real-world system. And the last slide, which is why we are entering a future where success belongs to those who embrace hybrid composable strategies, mixing and matching architectures like transformer, MOE, and so on based on the problem at hand. Architecture alone is not enough also. The real differentiator will be the foundational engineering. Organization that invest in solid data infrastructure, scalable platform, and integrated MLOps that turns innovation into reliable value generating system. Awesome. That's all for today's presentation, and now we can open up for any question.